Alright, let's consider a DSGE model approximated with first order perturbation techniques such that we have the following autoregressive structure for all our endogenous variables. Let's denote them with a YT. So those are the variables that you declare in the var block in the dynar mode file. And let's write them down in deviation from their steady state with a bar notation. And then we have seen that the first order perturbation solution has two matrices, Gx and Gu, and those will be multiplied to the model variables at t-1 in deviation from their steady state, plus the impact of current shocks times the perturbation matrix Gu. And we have talked about how to derive those Gx and Gu matrix for any DSGE model there is. Okay, so now let's, for the sake of simplicity, let's call this simply YT and this simply YT-1. So these are variables in deviation from steady state. And also we have the assumption, or let's make this assumption, that your shocks are normally distributed with a certain covariance matrix sigma u. Now in estimation, we are faced with the problem that even though we have n endogenous variables, capital, productivity, consumption, investment, etc., we typically don't have data for all the variables. So say maybe we don't have data on productivity or capital, but we do have data on output growth or investment or consumption growth, depends a little bit. So there are different variables that I can actually observe or match to data versus all the model variables that I need in my model. So let's call the subset of variables that you can actually observe by dt. And this is a subset of all your model variables. And let's also assume that maybe there is even some so-called measurement error. Okay, and let's say on average there is no measurement error, but there might be some covariance on the measurement errors, but it's also normally distributed. And UT and ET are orthogonal. Okay, they're independent of each other. Good. So these are the two important equations that we need to have a look at. But before we do this more closely, so I'm going to introduce notation to distinguish variables that are actually observable and variables that we are going to predict on given which information set. Okay, so first, a variable like dt, so a time subscript, is just a particular observation. A variable written like this with a superscript, a time superscript, means the whole set of observations or variables, the whole history of those variables. The third notation is going to be with the head. Those will be conditional expectations. And here we're gonna make use of time subindices, for instance t given t-1, and this will be equal to or defined by being the conditional expectation of yt given dt-1. So the whole history of observations up to t-1, and then the conditional expectation, the prediction for yt. Similarly, we're gonna call sigma t given t-1 as the corresponding mean squared error. Okay, so this is then the expectation of yt minus y hat t-1 times yt minus y hat t-1 prime given dt-1. so the conditional expectation of the deviations, of the squared deviations. And this is basically a mean squared error matrix, but we will also call this the covariance matrix conditional on dt minus 1. Okay, so this is the notation. This is where we are currently at. Now, how can we think about this in much more general terms? And we will think about this in a very important framework called the Gaussian linear state space system. So let's think about this for our model class. Now, basically, we already have such a system. Such a system is defined by a transition equation. How do I move from one state to the other? And we have variables that describe such movement, such dynamic movements. For us, these are the model variables, or in control theory, these will be called the state variables. So yt, gx times yt minus 1 plus gu times ut. And then the second important equation for Gaussian linear state space system is the so-called measurement equation. And this is how your state variables are linked to your control variables. And for us, control variables are observables. So dt is equal to steady state plus this H matrix yt plus et. Now the measurement equation links your model variables linearly to your observables. So basically your H matrix is just a bunch of zeros and ones. And most generally speaking, this is just a selection matrix H. There is measurement error possibly and a steady state for this. Okay, so this is my transition equation, my measurement equation. Yt in control theory is called the state vector, dt is called the control vector, ut are called the innovations, and et is the noise vector. Okay, so there's a little bit of different terminology in control theory or in statistics. For us, yt are our model variables, ut are our shocks, dt are our observables, and et are measurement errors. So we provide economic meanings to these terms, but they mean exactly the same. Now, you see linearity. We talked about state and space system, it's a system of equation. Now, Gaussianity kicks in here as well. Both our U's and our E's are stochastically distributed as normal processes. This enables us to derive the distribution of our states, but also of our observables, because linear combinations of Gaussian random vectors, such as ut and et, are also Gaussian. What does this mean? So this means that, let's plug in yt. This means that our data that we have, that is observable, is a linear combination of normally distributed variables. So it is also Gaussian. Okay, means dt is Gaussian. Now, a Gaussian distribution can be described by its first two moments, and that's all we need to know, by the mean and by the covariance matrix. However, in this equation, we already seen that the mean and the covariance of this distribution are dependent on the mean and covariance matrix of yt minus 1. And the problem I have here is that I do not observe yt minus 1. We don't have data for all the variables, but just a subset of those variables. And if we don't have that, I cannot construct the likelihood. If I have data for everything, this equation enables me to construct the likelihood, because everything is linearly Gaussian distributed, very easy to construct the likelihood. The problem that we're faced in this system is we don't have data for all the variables. And this problem is what the Kalman filter solves. Okay, so it provides estimates for the mean and the covariance matrix of the unobserved variables yt. If we have that, we can use that to compute then the likelihood. And the Kalman filter backs out these estimates from observed data, and it does so in a recursive fashion. We know Gx, Gu, sigma u, and sigma e, and the linear structure with Gaussian et and ut. We only have observed data d up to uppercase T, so my whole observations, and from which we want to infer the unobserved yt. Okay, so that would be yt, y1. All the values for all my model variables. Now, we will get recursive formulas for the first moment, so-called state forecast. And here our notation kicks in. Okay, so y hat t minus 1 and the state forecast error. Okay, we will denote this by the deviation from the true unobserved yt, what we will predict given conditional expectations. And for second moments, so this is the mean squared error or covariance matrix of the state forecast. And we're gonna call this sigma t minus 1 as given the notation that I've provided before. So the goal is to get formulas for y hat t given t minus 1, sigma t minus 1. That's the goal. And there is some algebra involved here to derive this recursive algorithm. Okay, so the goal is actually to get a recursive algorithm that then we can put into computer code. Now, let's start in period t equals 0 when no observations are available, and let's think about what can we say about the next period. So, and this is called the initialization step of the Kalman filter at t equals 0. Let's assume that the values for all my model variables at this hypothetical pre-period t equals 0 is also normally distributed with a certain mean and a certain covariance matrix. And I'm gonna use our notation for conditional expectations, but typically we don't condition on t minus 1 because there is no t minus 1. So you will very often find that this will be a normal distribution with some mean and some covariance matrix. But let's for now assume that we know these values. Okay, so in principle, again, any mean vector, any covariance matrix works here. Very often, though, for stationary systems, a convenient choice is to initialize at the unconditional long-run mean and covariance matrix of yt, which we compute from our state transition equation. Why? Because the solution that the perturbation approximation provides me fulfills the so-called Blanchard-Kahn conditions. In other words, the eigenvalues on this Gx matrix will be inside the unit circle, which is true by construction of the solution algorithm. So we can compute the unconditional mean from first order autoregressive process. Okay, this is what we have done so far many times. For 0 minus 1, let's call that mu y, which is the expectation of my model variables in deviation from their steady state, and this is of course 0. And the unconditional covariance matrix, let's call that sigma y, is the unconditional expectation of yt minus mu y, yt minus mu y, prime, which is then, if you plug it in, gx times sigma y, gx prime plus gu sigma u, gu prime. So similar to what we have seen in a vector autoregressive process of order 1. So this is a Lyapunov equation, easy to solve. You can use the Kronecker product to solve this analytically, or an efficient solver for this. Now, what does this imply for the distribution of d0? So d0 was the steady state plus h times y0 plus e0. Let's take the conditional expectation given information for t equals -1. So d hat 0 minus 1 is the conditional expectation of d0, d minus 1. Plug it in, evaluate the conditional expectation, what you know given your information set, and you are left with h times y hat 0 minus 1. That is the conditional expectation. What about the conditional covariance? So the mean squared error of d0 given information up to t equals -1. d0 minus d hat 0 minus 1. d0 minus d hat 0 minus 1 prime. Plug it in, develop terms, and you can notice that cross terms in E0 can be dropped because they are uncorrelated with everything else. So at the end, you will arrive at something that looks like this. Oh, sorry, I'm missing a condition on d minus 1 here. Okay, that is my conditional mean and the conditional variance now. This is our definition of sigma 0 minus 1. So this is h times sigma 0 minus 1, h prime. Sorry, there's a plus here, plus sigma e. Okay, now we have the distribution of d0. So d0 is normally distributed with this guy over here as its mean, and covariance matrix, this guy over here. Okay, let's try to find the conditional normal distribution of next period's data, d1, that is dependent on the conditional distribution of y1, for which we try to come up with a state forecast, y hat 1 given 0, and corresponding mean squared error matrix sigma 1 given 0. And we're gonna do this using the idea of a population regression. Okay, so there are many ways to derive the Kalman filter. I'm gonna stick to the choice of a regression coefficient, and because of linearity and Gaussianity, we know that linear or ordinary least squares coefficients have certain desirable properties. So the idea is, let's use a regression of the unknown difference between the true state and our forecast that we made yesterday, given new information that we get by looking at D1. Okay, let's set up a regression for some period t, let's call this today, given t minus 1 yesterday information. And let's say we want to look at how bad did we, or how well did we do with our state forecast, and compare that to our forecast for the data. And let's say there is a coefficient, a linear regression here. Let's call this LT, and maybe some error, some randomness here. Now, that LT is a regression coefficient. Eta is orthogonal to everything in the variables and contained in the information set at time t. Okay, now our forecast, that one over here, it's given from the state space equations. Okay, so d hat t minus 1 is d plus h times y hat t given t minus 1. Let's define the forecast error with little a. So that is dt minus d hat t given t minus 1. So that would be d minus d bar. Plug it in. The implied regression equation is then given by... Now, the problem is we don't have the left-hand side. We don't have data for yt to actually run and compute the regression coefficient lt. But let's go forward with this. If we somehow knew lt, so it's a linear regression and we get like the best linear unbiased estimator for this lt, we could, if we knew this, we could form a forecast of our forecast error for the state. Now, what is the general formula of a regression coefficient? Just as a reminder. All right, expectation y in matrix form, that's the general formula for a population regression coefficient. In our case, so LT is the expectation of y and x, so left-hand side, right-hand side, all right? Right-hand side, dt minus d bar minus h y hat t minus 1 prime times the expectation of dt minus d bar minus h y hat t minus 1 prime dt minus d bar minus h y hat t minus 1 and the inverse of that guy. So sorry, I had a mistake here. The expectation, it's the inverse of that expectation up here. Okay, now let's combine terms, make use of notation and rearrange a little bit. I'm not gonna do all the algebra here, but we can re-express this equation in terms of our variance matrix sigma t given t minus 1 h prime h sigma t minus 1 h prime plus sigma e, the inverse of that guy. Now, my population regression coefficient LT here is a function of values that we have already computed. That is quite interesting. We know this in period t, we have made this prediction and the mean squared error covariance matrix, so I know the right-hand side. So for period 1, my L1 becomes... Now let's do the state forecast. So given our best forecast for the state today at time 0, our best forecast for tomorrow's state, y1, what will that be? So y hat given 0, that is, again, remember the conditional expectation of y1 given d up to 0 will be equal, plug in the equation for that. Gx is not, there is no randomness to this, it's always the same matrix there. The conditional expectation for next periods, shock is always 0, given information today. So what we are left with is y hat 1 given 0 is gx times, let's use our notation for this, y hat 0 given information at 0. That's one key equation right here. Let's at the same time, let's rewrite the state transition equation. So we can also write y1 in, this is the state transition equation. Now let's do a trick. Let's add and subtract the same thing. So let's add gx times y hat 0 given minus 1. And let's subtract the same thing. So we can rewrite the first guy as gx y hat 0 minus 1 plus, let's have a look at this guy over here. There we have it, y0 given -1. So we can plug in this over here. Okay. And we're missing gu times u1. And of course we have to put this to 0, this to 0, and this to 0 minus 1 plus that eta. Let's try to forecast tomorrow's state given information until time t. So y hat 1 given 0. Again, that's the conditional expectation of y1 given d0. Given this equation, so that will be gx. That's already the forecast there. Fine. Plus, sorry, I'm missing something here, of course. The gx. Right there. So plus gx times L0 times d0 minus d minus h y hat 0 minus 1. The expectation of the residual given information is always 0, okay? It's orthogonal to everything, and the expectation of next period shock given information at t equals 0 is also 0. So I'm left with that term, gx times L0, d minus that guy. And this over here has a special name. It's actually very often denoted by a k or k0, which is the so-called Kalman gain. This allows us to forecast tomorrow's state just based on yesterday's forecast and today's observation. Right here, I can forecast tomorrow's state, information of today. And what do I need for this? I need yesterday's forecast and today's observation. And that matrix K, let's call that with a T, is gx times LT is gx t given t minus 1 h prime h sigma t given t minus 1 h prime plus sigma e, the inverse of that. That is called the Kalman gain. It determines by how much your state estimate is updated based on your previous forecast error. Now, so much algebra, you probably don't see the big picture yet, but this actually enables us to have a look now at the full distribution of y1 given d0. That will be normally distributed y hat, y given 0, and sigma y 0. That guy, there it is. We have just computed that. This is all, the right-hand side is completely known to you, so you can compute that. Now, what about the covariance matrix? So we need to find or derive that mean squared error matrix sigma 1, 0. And we're going to do this from the state forecast error. So we need to first come up with a representation of the state forecast error. Let's plug in gx times y0 plus gu times u1 minus y hat 1 given 0. Let's plug in the just derived equations and rearrange a little bit, and you can come up with this representation. And the covariance matrix sigma 1 given 0 is the conditional expectation of that formula times its transpose, given information up to t. Now, plugging everything in, rearranging terms, noting again that u1 and e0 are orthogonal to cross terms, and we can do some algebraic things. I have the steps, the required steps in my notes for you. Here, I just want you to provide the end formula that we can get. Okay, so this is some not hard, but a little bit tedious algebra. We can simplify this to get the following equation. And the beautiful thing about this updating equation right here is, again, the right-hand side is stuff that we know. So to update the covariance matrix sigma 1, 0, we only require knowledge of the previous period's covariance matrix and the given matrices of the state space system. So we have everything for y1 given d0 is normally distributed, y hat 1 given 0, sigma 1 given 0. Now this was going from 0 to 1. Now we could go to 2, to 3, etc. So there is the recursiveness kicking in. So in general steps, the distribution of yt plus 1 given up to t information set is normally distributed with y hat t plus 1 given t and sigma t plus 1 given t. And the formulas to compute y hat t plus 1 given t, these are given like that. So, and this is here, if you remember, this is what we defined the forecast error, little a. So this is what we think dt will be. So this is d hat t given t minus 1. Compare that to dt, this is the forecast error. Kalman gain times forecast error is needed for y hat t plus 1 t, and sigma t plus 1 given t is that formula that we've just seen. Okay, so these are the, very importantly, closed form expressions for the state forecast y hat t plus 1 t and the corresponding covariance matrix sigma t plus 1 given t. Now let me summarize this algorithm. The problem the Kalman filter solves is that we only have observations for dt, but we don't have observations for yt. And what the Kalman filter provides me is a best estimate for these unobserved variables. And what we make use of is Gaussianity and linearity. This enables me to derive basically the best linear and unbiased estimate for the state variables or our model variables. And we do this recursively. So we initialize y hat 0 minus 1 and sigma 0 minus 1. Whatever you want to do, a good and a convenient choice is to initialize this at the unconditional distribution of your model. So since y is in deviation from steady state, this is basically a vector of zeros, and this is the solution to the Lyapunov equation for the state transition equation. Then for t equals 1 to t, so this is a for loop. First step, compute the Kalman gain. So kt is gx sigma t t minus 1 h prime times that parentheses, the inverse of that parentheses, and I'm gonna call that with a big omega, so that, remember what is inside that parentheses is this over here. So maybe you should probably compute it the other way around, right? First compute this omega. We will see that omega has a special meaning. Right hand side, we know this matrix. We initialized that, so we know this matrix. No, everything is known. So this is known, everything is known here. I can compute everything. That's the first step. Next step is compute the forecast error. So AT is dt minus d bar minus h y hat t given t minus 1. Third step is compute the state forecast for next period given today's information for t plus 1. So y hat t plus 1 given t, and update the covariance matrix. So sigma t plus 1 given t. So this is the Kalman filter. How does this help to compute the log likelihood, well, let's say just the likelihood for now, P of all my observations? And the answer to this is everything that I need is a byproduct of the Kalman filter, which is pretty cool. So let's have a look at this likelihood function. Okay, so P of dt up to d1. As we have seen in vector autoregressive models, let's factorize this likelihood function. So we can write this down as dt given dt minus 1 times f of dt minus 1 given dt minus 2 times times f, sorry, it should be p. So p of d1 given d0 and p of d0. From dt being equal to my measurement equation, right? H times yt plus et, we can compute or infer that this is normally distributed of d hat plus h y hat t minus 1. And we've done this for the very first period above, that covariance matrix, and that we called omega. So, in a sense, that likelihood contribution, each individual likelihood contribution, for the first one, we know we've derived it even in closed form because we initialized the very first value. So this was 0 given minus 1. So we know that value. And each of those entries are normally distributed with that as a mean and that as a covariance matrix. And as you can see, this is given by the Kalman filter and this here as well. So everything that I need to compute the distribution of each contribution right here is a byproduct of the Kalman filter. Now, because this is normally distributed, we can even write down the density function. So let's write this even down, which is 1 over the square root of 2 times pi, number of observations, raised to the power of number of observations, the determinant of your covariance matrix, times the exponential of minus 1/2 dt minus d bar minus h times y hat t minus 1 prime omega t, the inverse of that, times that same guy over here. And if you have a close look at this expression, we call that the forecast error. So basically, this is the forecast error. So I can simply write AT prime times AT. So I have the density function for each contribution to the joint likelihood. Taking logs, you get the log likelihood function. Okay, you can also, of course, have the log likelihood function, which is what we work with in the codes because it's numerically easier to work with sums instead of products. Okay, and this is the very famous formula that you see, minus number of observations have times the log of 2 pi minus 1/2 the log determinant of omega t minus 1/2 at omega t at. So let me reiterate, the Kalman filter delivers everything that we need to compute the likelihood as a byproduct. Now, a little side note, so far we have looked at the Kalman filtering recursions to get so-called filtered variables. That is the best prediction for tomorrow's state given today's information. But we can also compute an estimate for today's state given today's information without deriving this in detail. It's that equation right here, and the corresponding mean squared error looks like this. So there's our omega again times h sigma t minus 1. More importantly, maybe we're also regularly interested in estimating not only the model variables, but also the shocks. So once we have estimates for the model variables, we can also filter out the shocks. And we can do so in a similar way, but we can also do it in a different way that is called smoothing, where we have a different observation set, not just current period, but let's take into account the full information set, okay? And this is what the so-called Kalman smoother provides you. So you can get out y hat t given all informations. And this also provides you means to give you estimates for your shocks or your so-called smoothed shocks, which is also quite interesting. I don't tell you the formulas here. They are done by backward recursion. So filtering is forward recursion, smoothing is backward recursion. So this is my first side note. My second side note is what is in the DSGE literature known as stochastic singularity. Now, if you have noticed, we are required to compute the inverse of this omega matrix. Okay, for computing the likelihood for sure, but also right here to compute the Kalman gain. And an inverse can only be computed if we have a non-singular matrix. So whenever you're faced with a situation where this omega is a singular matrix, you have what is basically called either a numerical problem or stochastic singularity. So for instance, there are some requirements to not run into this issue of stochastic singularity. Okay, so stochastic singularity is we need to compute omega t, the inverse of that guy, and we require a couple of things for this. At least as many shocks plus measurement errors as observables. You can have more shocks and measurement errors. That is not a problem. And the major thing that you have to be careful about there you cannot have collinearity between your observables. So importantly, think about a typical budget restriction in, say, an RBC model. If you declare all three variables as observables, you will run into this stochastic singularity problem. So you cannot compute the inverse. You will get errors, numerical errors. So that is what you need to keep in mind. And my last side note is, why is Kalman filter the best? Now, in the derivation above, we have made use of a population regression idea. We have linearity, we have Gaussianity, and from our undergraduate econometrics courses, we know that given certain assumptions on error terms, ordinary least square estimator is best linear unbiased. It's blue, okay? And this is the same here. Because all the assumptions for this blue criteria are fulfilled, the Kalman filter is the best estimate that I can give you in the class of linear estimators. And that is why the Kalman filter is not only analytically popular, but for us, even more importantly, in computational terms, I have closed form expressions. It's just a bunch of matrix equations. In inverse, that's the toughest problem. And that's it. Okay, it's really easy to compute, it's extremely fast, and it provides you everything that you need to compute a likelihood as a byproduct. And it is best in the class of linear Gaussian state space systems. All right, so this is the theory on the Kalman filter. I've skipped several derivations or mathematical algebra. There are some notes on this if you are interested in this. At the end, it's an algorithm. It has a couple of steps that you can easily compute yourself. And that is exactly what our next step is. Okay, so let's write such a Kalman filtering function. What are the inputs? What are the outputs? How can I write this for loop? And I'm going to use MATLAB for this. All right, now let's program a function. Let's call this DSGE Kalman filter. And we need to think about the input and the output arguments in a moment. I usually do this later. So first of all, we've discussed that we need to initialize the state vector somewhere. Okay, this is rather arbitrary, but good practice is to initialize the state vector, the y hat, at the stationary distribution. So let's call this y hat 0 given -1, but let's keep the notation here for tm1. And we know that since this is in deviation from steady state, this is just a bunch of zeros and number of elements in y. So I guess at some point I also need to get dimensions. Okay, so I need to get somewhere ny. What about the covariance matrix? Well, this is defined as sigma t tm1, and we know that we can use the solution to the Lyapunov equation. I've already copied our function for solving Lyapunov equations, and here I need to enter gx and gu times sig u times gu prime. Okay, this is usually very fast. You can also use the Kronecker product. So the DSGE Kalman filter, what I want this for is to compute the log likelihood contribution for t given t-1. So for t given tm1. So that is for sure one output argument that I want to use. And as you can see already, input arguments are for sure the state space matrices, my shock matrix, and maybe I also have measurement errors. Okay, that is for sure in here. And remember, we did have that H matrix mapping states to observables. We probably will need data. Let's call that D. Okay. Now, where do I get ny? I could get ny, for instance, from the dimension of my state space matrix. I'm probably also going to need number of observations and the number of observables that I have. I can back this out from D. Okay, so in terms of dimensions, I'll expect D to be the data matrix with rows corresponding to time periods and columns to observables. Good. Okay, so we have initialized the state vector, and let's also initialize the output argument, so tm1. This will be, I always like to use nan, so I always know if something went wrong in the computations. Okay, now let's do the Kalman filter recursions. Kalman filter recursions. So this is a big for loop, and this will go over all your observations. And remember, we had put forward different steps. Okay, so there was step 1, compute the covariance, or compute omega. We call that omega, and the Kalman gain. Compute Kalman gain. Let's just call it like this. Then there was a step 2, compute the forecast error in observables. Step 3, that required us to compute the state forecast for next period given today's information. And step 4, update the covariance matrix. So that was the Kalman filter, and then we sort of need to look how we can use objects to compute the likelihood contribution. So let's start with the first step. Here, the first equation that we had in our notes is we need to compute this big omega matrix, and that was the formula that I've written down several times, times h prime times maybe a plus, maybe I have measurement errors. This is sometimes called just the gain matrix. Now the Kalman gain, let's call that K, is gx times sigma t tm1 times h prime times the inverse of omega, and we're gonna use MATLAB's multiply function that is more robust than times inverse. You could do that, but this usually performs better. So this is the Kalman gain. Okay, that's it. Now let's compute the forecast error. We call that A. And here we needed to take dt. So this is in period t, all my observations. And if you have a look at the formula, it was that we had the steady state of d plus h times y hat t m1. Now quickly have a look at your dimensions right here. So y hat tt minus 1 is a ny by 1. It's a vector. Times h makes this a nd by 1 vector. This is nd by 1. But your data is, I pick out a row and then take all the columns. I need to make this a column vector, so I need to take the transpose here. Step 3. Let's compute the state forecast. That is y hat. Let's call this t plus 1 given t. That was just gx times y hat t minus 1 plus k times a. And update the covariance matrix. So sigma t plus 1 given t Let's write down the formula that we've developed. K times H times sigma TTM1 times Gx minus K times H transpose. And now I have initialized this. So I have initialized y hat t, so y hat 0 minus 1, sigma 0 minus 1. Then I'm gonna start to compute y hat 1 given 0, y hat, sigma 0 given 1. And then for the next period, I want to iterate on that. Okay, so the trick, let's reset the values for the next time step, meaning y hat t minus 1 becomes y hat t p1t. And the same for sigma tt minus 1 sigma. Okay, so if I put this as at the last lines of the for loop, it's gonna use that correctly for the next time step. Very good. Okay, now let's really quickly have a look whether I need more input arguments. I have data. There is one that I need, the DSS. So I need to use that as an input argument here as well. Now, so far so good, but I have not used anything of those results for computing the likelihood. Okay, so before we reset the values, let's compute the contribution to log likelihood. Okay, so this is, what did we call that? That was that guy in period t, and this was the formula for the density of a multivariate normal distribution minus number of observations divided by 2 times log times 2 pi minus 1/2 times the log of the determinant of omega and minus 1/2 times a prime, the inverse of omega times a, right? And that's basically it. Okay, that is a well-written Kalman filtering routine. Now, there are many things that you can improve in this function. So for instance, you have to think about stuff that can go wrong. What can go wrong is the inverse of omega and is also the determinant of omega. Okay, so if it is a singular matrix, then this will not be, we're not going to be able to compute that. So what I like to do is, at this point, I'm actually going to compute the determinant of omega. And if this one is going to be negative or 0, it's not positive definite, okay? Then I'm going to catch this and I'm going to do something that is very simple. I'm going to put a penalty term on my log likelihood. Let's put a minus 10 to the power of 8 and return stop the iterations. If everything went well, I'm going to compute the Kalman gain. Okay, so in a sense here already back there, I do not have to compute it again. I can use that one. Okay, we need to test this. Okay, let me save this function and call that DSGE Kalman filter. Okay, we need to test this function. So let's use a basic RBC model. Okay, so let me have a couple of variables for a basic RBC model. I'm going to write a dynar file just to pre-process the model and to solve the model. But I'm going to compute the likelihood, not with dynar, but manually with my function. So let's declare a couple of parameters and a bit one shock, standard RBC model. Let's provide a calibration, some values for the parameters, then the equations for the RBC model that we've seen in class. Very good. Let's compute the steady state either analytically or with initial values. I'm gonna do this analytically, so I'm gonna provide a steady state model block. Let's compute the steady state. Bam. And then let me save that and call this RBC for estimation.mod. MATLAB doesn't like me saving MOD files. Then let's do it like this. And let's run Dynair 6.2, add the MATLAB folder, Dynair RBC. Let's see whether all is well. Yep, I can compute the steady state, no errors. Really good. So let's use this model and simulate data. Okay, and we've seen that there is a command called stochastic simulations that uses first order perturbation approximations to get a linear state space system, and this is then used to simulate 200 data points. Now I'm gonna store data from these simulations. That is, the simulation will be, let me run this first. Nothing happens, of course, because I have no stochastics in the model yet. So I need to add stochastics. So I need to tell Dynair what the covariance matrix of the shocks are. I only have one shock, so that's easy to define. And then I get IRFs. Great. And I get simulated data, and the simulated data is stored in OO_endosimo. The columns are time periods and the rows are the variables in the way you declared them in the var block. So let's say I want to store the data for output, consumption, and maybe investment. So I need to get the first, second, and last row. Now, since this is poor MATLAB code, I'm gonna put this into a verbatim block so Dynair does not try to interpret these dots and so on. And I'm gonna save that in RBC data. So I have a file that I can use this. Okay, now let me run this and you will find a MAT file that has 200 observations for these variables. Great. Now let's see where we can, or how we can test our function. Okay, so let me open up another script. Here I'm saying run the mode file, and then I want to evaluate my Kalman filtering function. So I need a couple of things. I need to get the data. Well, that is easy. I can just import the data. And remember, we have one shock. I'm just going to use one observable. Feel free to play around with which variable you take. So data is, in a sense, a 200 by 1 matrix. And this is my input, my first input. Great. Then I need to get the steady state for my observables. So I need to back out from Dynair stuff, and what we are going to use is the information that Dynair produced on the decision rule or the policy function already. This is all stored in OO_dr. So let me store that. Okay, so actually Dynair already computed my state space matrices and the steady state of the variables right here. Okay, so I can access the ys, so dr.ys. This will be the steady state that is computed when Dynair solved the model. There is also OO_steady state, which, if you have a steady state model block, will be the same numbers. If you have an init-val block, these will be your initial values. Okay, so your Y0 for a numerical optimizer. Let me store that as into the DR just because I will need this later on. And even though we have a stochastic model, so the steady state for the endogenous will always be 0. And this is stored here in deterministic contexts. This might be different, but let me write this down. This is the init val for the steady state of shocks. This is the init val for the steady state of endogenous variables. And this is the information on decision rule or the policy function computed by Dynair. Now this is what I called in my notes y bar. Okay, so this is the steady state for all the steady state of endogenous variables after I've run the numerical optimization or after the steady state model block was evaluated. This is also the point where Dynair solved the model. Now I need DSS, or let me call that a D bar. Why not? That is basically y bar, but now I need to select observables. And actually, let me do this in the mode file, because we will compare what we did with our Kalman filtering routine, what Dynair can do. So Dynair has another block where you tell Dynair what variables are observable. And this is similar to the var command. You simply tell the name of the variable. And if I now run Dynair, I have a new options var ops. This will tell me which variables I declared as observables and the ID of that variable. This is quite handy because I can use this guy over here to access the steady state of my one observable variable. If you have several, this will be a vector. Okay, and I can then plug in this guy over here into my Kalman filtering routine. Now next I need to find the selection matrix which picks out the observables from my endogenous variables. Find the matrix H in the measurement equation. Okay, which selects observables from endogenous. So in this matrix, let me also store this in the decision rule because this does not change. Let me initialize this. This has number of observables, so length of options var ops id, rows, and endogenous variables as columns. And now I want to put a 1 in the column where y is. Okay, so m handle names. This is the way I declared the variable. So I want to put in the first column a y. And I'm gonna do this. Say if you have more than one observables, I'm gonna run through the observables, and I'm just gonna put whenever I'm just gonna put in the corresponding column a 1. So if I run this, I have found my H matrix. Okay, just for illustration, let's say we're going to observe 3 variables. Then let me run this again. Your DRH matrix will be looking like a matrix, and this is then Y, this is K, and this is C. Okay, great. But I'm just gonna do one observable right now. Good. So I have my H, so I can plug in right here DRH. Now I need to find my GX and GU matrix. So now I need to set up the state space system. Okay, and importantly, Dynair's DRGHX is basically my GX matrix, and Dynair's GHU is basically my GU matrix. But Dynare has a different ordering of variables. Okay, so let me write this down just as a reminder. Dynare's GHX is in so-called decision rule order, where the static variables come first, then predetermined ones, then mixed, then forward-looking ones. I'm just gonna keep things simple. I want everything to be in declaration order, meaning the way I declared my variables here. So the second row will always correspond to consumption. So I need to transform this. So Dynare's GHI is in DR order and also contains only columns for the state's variables. In Dynare, those are predetermined and mixed variables. So the variables that you define in your mode file with a -1, -2, whatever, those are the state variables. But my GX matrix, I want this to be number of endogenous times number of endogenous. And then I'm gonna fill the columns for the state variables with what Dynare computed. So first comes static variables and then predetermined and mixed, and Dynare has a number for that. Those are predetermined and mixed variables. So I'm gonna fill the 9th and 10th column with GHX. Okay, so fill in solution. This creates full Kalman or state space transition matrix. This fills in the solution. And lastly, I'm gonna put this in declaration order. So I'm gonna overwrite GX. Dynare has a vector called inverse order var, which tells me how I need to permute the rows to get back from the DR order to declaration order. And I need to do this on the rows, but also on the columns. Okay, so this is put into declaration order. What about Dynare's GHU matrix? That is in DR order, but I don't need to care about the columns, so I can simply say GU is dr.ghu, dr.inverse order var. Great. Okay, now I have a GX matrix, looks like that, and a GU matrix, looks like that. So I have a GX and I have a GU. Now I need information on my shocks. So let's extract information on shocks and measurement errors. And this is quite easy. Dynare stores the covariance matrix of what you declare in a shocks block in m_sigma_e. One shock, this is the covariance matrix. And the covariance matrix of measurement errors, that is stored in m_h. If this is just a 0, even if you have 5 observables, if you don't declare measurement errors, then this will always be a 0. So let me catch this case. If is equal mh, 0. Let me create there are no measurement errors, but let me have the correct dimensions here. That will be the number of observables that I have. Var obs id, the length of my observable vector. Else, this should be equal to m_h. So I have SIGU. Okay, so running this, no errors, great, and hopefully no errors here. Unfortunately, there is an error. So line 11, let me go in here, obs, yeah, that should be number of observations. Okay. Bam. Now, these are my likelihood contributions. And the log likelihood, so log likelihood, that is just the sum of those contributions. Now, of course, this might change. Say, for instance, you change the parameters in your model. Let's try out something different. Let's set the values for parameters. Okay, and then there you do this in the m_params structure. Those are all my parameters as I've declared them. And let's say I want to change the alpha to something else. I don't know, something like 0.2. And I want to change the delta to 0.025. And I want to change the rho to 0.5. Maybe I also want to set the shock parameters differently. Okay, so maybe I want to change that to 1.5 squared. Okay, and maybe I want to add a measurement error. Let's stick to the no measurement error convention here. So let me now change the parameters. Okay, meaning I need to compute or recompute the steady state and perturbation solution. And Dynair has a very simple command for this called resolve. Don't worry about the 0 here. It needs to get information on the parameters. If you change any parameters here, don't worry about options. It needs information on the state space system and initial values for your steady state if you use an init val block, endogenous and exogenous, and there are also ways to deal with deterministic exogenous variables, but we are not going to do this. So I've computed a new solution. We need to check whether the solution is valid, and whenever the info matrix is 0, all is good. Okay, so whenever this is non-equal to 0, okay, so something wrong with steady state or solution. Not gonna go into detail what values are possible here. So actually I could say my error, something wrong. Could catch that. Okay. So once I have a new steady state and a new perturbation solution approximation, I can rerun everything. Now let me reorganize myself a little bit. So the likelihood will be a function of the parameters and maybe some options. Okay. So let me sketch code how I'm going to arrive at a likelihood. So data is always the same. Okay, so let me put this right here. Also, my selection matrix will always be the same. Good, and everything else comes into, let me cut this and into a new function. I'm gonna call this function DSGE log likelihood. And this is going to be a function of, I don't know yet, right? We'll see. So I have this run script where I run the mode file, I preprocess it, I get initial values. Maybe I'm gonna change values. So let me put this guy over here into something that I'm going to call xparam 0. The first parameter I want to change will correspond to alpha. The second parameter that I'm going to change will correspond to delta, and the third one to rho. And those are the parameters I want to estimate, okay? Or I want to change. Maybe not all of the parameters, but at least a subset of parameters. This is basically my initial guess. And once I have that, right, I want to call my likelihood function. What was it called? Right here, DSGE log likelihood, to compute my log likelihood. Okay. So let me again reorganize myself a little bit. So I'm going to load in the data. The selection matrix is always the same. And here I'm going to provide initial guess or initial values for parameters I'm interested in. Okay, and I'm gonna provide them to my likelihood. And of course, I'm gonna need to provide data. I need to provide information on the decision rule, information on the model, and options. Information on options. Okay, this is the dynamic structure for options. So this is basically my new function DSG likelihood, log likelihood, and it should output the log likelihood. Okay, so I have changed parameters. First thing I need to do is I need to recompute everything. So I need to set the parameter values as we did just in the other script. So I need to update the parameters for alpha. That was my first. I ordered it first for delta and rho. Fine. Maybe you also did something for your variance. This could be x param 4 or so. I did not change that. And maybe you need to update your measurement errors. Go ahead. Now we need to recompute the steady state and the perturbation solution. Note that the R goes in here and the R comes out here. The H matrix, let me store that because it gets overwritten. So this solves the model, and if something is wrong, I'm going to put a penalty on my log likelihood. So let me call that penalized likelihood, and let me define the penalized likelihood as minus 10 to the power of minus 10 or so, or 8, whatever. Very small number. You could also use minus inf. Okay. So x param are my inputs. I'm gonna update the model parameters, the shock parameters maybe. I'm gonna recompute everything, and then I'm going to set up my state space system. So I'm gonna get out the y bar, I'm gonna get out the d bar, and I'm gonna get gx and gu, get my sigma u and sigma e, run my Kalman filter, sum everything up, and all is good. Well, if something does not work as planned, if something went wrong, then I will have NaNs here, or maybe this is imaginary or infinity. So let me catch all those cases. So if it is infinity or NaN or imaginary, then let me penalize this. with a very, very small number. Okay, so this is a small number, can also be minus inf. And main function end. Okay, let me save that, DSGE log likelihood. Let me go back to my script right here. Let me see whether I'll get errors. Yeah, here I simply pass on the H matrix. Okay. So let me rerun it. And I have computed the log likelihood. I can now play around. So let me put this to 0.5. What is the log likelihood value there? Okay, great, 0.1. And what I'm basically doing here already, I'm trying to find the best values for alpha, delta, and rho that will maximize the log likelihood. So instead of me trying out all these different things, let me run optimization. Okay, so let me ask an optimizer. So like fmin unc, unconstrained, on a function f, and these are my starting values, something like that. Okay, it works on the starting values, no error, fine. And I would like to use this on a function f. So let me define this function f is as an anonymous function, as we've done with the vector autoregressive maximum likelihood estimation. This is the log likelihood. I want to maximize that. Optimizer always want to minimize, so I'm going to multiply this with -1, and this is going to be this function right here, and the x should go in here. I'm going to pass on always data, always the information on the R, M, and options. Okay, this is a function handle to hand over additional parameters and multiply. Oh, sorry, this is not the function handle. Okay, so use function handle to hand over additional inputs and multiply by -1 for negative log likelihood. That's the idea. All right. And then I can run that and I will get out the optimal x and a function value and an exit flag and some additional outputs. I don't care about the gradient at x, and maybe I'm not interested in the gradient, but I might be interested in the Hessian, because this is a gradient-based optimizer that is used here. So something is wrong right there. It tells me unrecognized field name GHX. So this basically hints towards Dynero did not compute the solution, but I thought I caught this. So right here, if something was wrong, I'm gonna penalize that. Oh, of course, I'm gonna stop the computations. I'm gonna end the function. So I need to end a return. Otherwise, it's going to try to compute these things. And of course, GHX, GHU is not there. Great. Let me run this and let's see. Done. I have a function value. This is the negative log likelihood. And these are the values for the maximum likelihood estimates. Right? And let's see where the true values was 0.35, 0.10, and 0.9. So how close is this? Well, let's compute this via the Hessian, the standard errors, right? I can use the inverse of the Hessian take the diagonal elements and take the square root on that, and I get standard errors for my estimates. So let me call that SE. If you use an optimizer where you don't have the Hessian, you can use the Hessian numerical function that I have provided you with. So let's use that Hessian. It's basically, it should be the same, roughly the same. Not but close to the Hessian here. And then let's display the results. So I have alpha, delta, and rho. Let's display point estimate, standard error, t-statistic. Parameter names are my rows in this table, estimate, standard deviation, and t-statistic. There you go. You have a maximum likelihood estimation. Now, this is what we did manually. Dynair, of course, can do this for you. Okay, so let me go into my mode file. Let me show you how you do a maximum likelihood estimation in Dynair. So you told Dynair what variables are observable. Now you need to tell Dynair which parameters you want to estimate. So I want to estimate alpha. Let's provide initial values. Let's use the same ones that we used here. So 0.25, 0.25. Delta was 0.2. And rho was 0.5. This is the initial value. You can also select a lower bound, comma, upper bound. Okay, makes sense to bound them. But you can, of course, try different bounds. Or if you don't put any bounds in here, that will be minus infinity and plus infinity. Okay, let's keep it like that. And then you call the estimation command. You need to tell Dynair what is the data. That is called rbc data.mat. Comma, which optimizer do you want to use? fmin-unc is the optimizer with the number 1. Have a look in the manual, and that's it. Okay, so if I now run Dynair, it does the optimization, and this is the result from my maximum likelihood estimation. So let me run the whole script now to see how close we are. So this is Dynair's maximum likelihood estimation, and this is our maximum likelihood estimation. We use the same initial values, we use the same numerical optimizer, and the same way to compute the Hessian. The function, the Hessian numerical function, is exactly the one used by Dynair to compute the Hessian. And yeah, that's it. Maybe one little comment or one little side note. Dynair has a much more sophisticated way to compute the likelihood via the Kalman filter. It uses several tricks to deal with problems like computing inverses and determinants. And also, Dynair is much more faster in its Kalman filtering routines because at some point, this Kalman gain, or this omega, does not change really. It converges to a matrix. And Dynair catches this convergence, so it, whenever the Kalman gain converged, and this typically happens in these models after a couple of periods already. It does not need to recompute determinants or inverses, and this is so much faster, even though the likelihood will be a little bit different in terms of values, but it doesn't change the optimization of the likelihood. Okay, just a side note, this is like a very textbook way to compute the Kalman filtering recursion. If you want to have a look what Diner does, you can have a look at Diner's Kalman filtering routine. Okay, this is, it even can deal with non-stationarity of some variables, and yeah, can do many things, but at the end it does the same thing. It computes forecast errors, your omega matrix, then it computes basically the determinant of your omega matrix in a fancy way, the inverse of your omega right here, and then it computes the likelihood contribution. There's the Kalman gain. There you go. And at some point it can also call the so-called steady state Kalman filter. If the Kalman gain has converged, then there is another function which is called, which is so much faster than recomputing inverses. Okay, all right. I hope you understood the way that this works. Let me summarize this real quickly. There is a function that computes the log likelihood contributions using the Kalman filtering recursions. There are 4 steps to this, or 5. You need to initialize the Kalman filter somewhere. You need to compute the omega and the Kalman gain matrix, the forecast error, the state forecast, the updated covariance matrix, and then compute the likelihood and iterate on this. So this function gives me the log likelihood. Now I have another function which calls the Kalman filtering routine, right? For any change in parameters that I want to do, for data, information on my decision rule, some model information, some options. And here, very importantly, I need to, whenever my parameters change, steady state changes, the solution, the GX and GU matrix will change because they are Taylor approximations at the steady state. And Diner, we're just going to use Diner's little resolve functions here to recompute stuff, update the parameters, recompute the solution, and then set up the state space system, everything that we need to call our Kalman filtering routine, and then sum up the contributions, check whether everything is wrong, and put out the value for the log likelihood. And how do I do maximum likelihood? Well, I take the negative log likelihood and I'm going to minimize that using any optimization algorithm that I want to do. Then I have the point estimate. The standard errors are computed via the inverse Hessian. On the diagonal, I have the variances. Square root of those are standard errors. T-statistics. Put everything in a nice little output. Good. So this is how we can estimate any DSGE model with maximum likelihood.